So here let us go to the new unit in physical chemistry, that is electrochemistry. What is all about electrochemistry? Let us go to, that is introduction. In the introduction, that is electrochemistry, it is a branch of chemistry which deals with branch of chemistry dealing with electrochemical reactions and electrochemical cells. What do you mean by this electrochemical cells? Electrochemical means, when you say electrochemical, I'll say electrochemical reactions. Here two types of conversions takes place. One is if chemical energy is converted to electrical energy. If chemical energy is converted to electrical energy, the process we call it as electrochemical process. Electrochemical process. This electrochemical process is always spontaneous. On the other hand, if the electrical energy is converted to the chemical energy, then such process we call it as electrolytic process. Electrolytic process is always non-spontaneous process. So what is happening here is, in the case of the electrochemical process, when you say the electrochemical process, when you are saying electrochemical process, in the electrochemical process we find that it is spontaneous. If it is spontaneous, it should obey the condition of the delta G is equal to minus NF of E. Minus NF of E of cell should obey, where delta G is the amount of useful work which is used to carry out the various applications, to run a motor, to run an engine, mechanical engines, and so on and so forth. So that means what is happening here is, so there's a slight change between the electrolytic process and electrochemical process. There's a slight difference is there. So when you go for electrolytic process and electrochemical process, what are the differences where we can carry out for the electrochemical process and electrolytic process? We are going to study through comparing and contrasting points. So here, if you go to the difference between electrochemical process and electrolytic process. So first of all, what I would like to do here is, I am going to give you one small differentiating table here. If you take electrochemical process, an electrolytic process. Electrolytic process. So here the differentiating points between these two is the principle involved here is the principle is the electrochemical process. Chemical energy is converted to electrical energy. Chemical energy is converted to electrical energy. In the case of the electrolytic process, principle, if you take, what is the principle involved here? Reverse of that, electrical to chemical energy is the first differentiating point. Then second one, if you take here, electrochemical process is always spontaneous. It is spontaneous. Do not need a battery. That means it doesn't require any power source. In other words, what I mean to say is that electrochemical process does not require any power source. So no battery is used, no external power source is used. If you go for electrolytic process, yes, it is non-spontaneous. It is non-spontaneous and needs a power source. That is nothing but battery. Third is, in the electrochemical process, if you take, both of them are redox reactions, both involve redox reactions. Electrochemical process involves redox reaction and electrolytic process also involves redox reactions, but only thing is that there is a slight difference. When you go for the electrochemical process, redox reaction again involves two electrodes, that is anode and another one is cathode. If you go for anode in the electrochemical cell, anode of course the process taking place at anode is oxidation, and the process taking place at cathode is reduction. So if you go for cathode, if it is reduction, the sign convention is anode is negative and cathode is positive here in the electrochemical cells. So here anode is given negative sign convention and it participates in oxidation. Anode electrode is given negative sign convention and it participates in oxidation, and cathode is given positive sign convention and it is given participating in the redox. It is participating in the reduction reaction, and the process is redox reaction. And why here anode is given positive charge means you can say that it depends on the activeness of the electrode. If an electrode in the electrochemical cell, whichever electrode is active, that electrode undergoes oxidation, and whichever electrode is less active, that electrode will undergo reduction. So here at anode always the electrode is active in the electrochemical process. That's why all active electrodes, they participate in the de-electronation, that is they lose electrons and the ions goes into the solution. But in the case of cathode electrode in the electrochemical process, because of its inactiveness, it participates in the reduction. It accepts the free electrons coming from the adjacent electrode, and it gets reduced and it gets deposited at the cathode electrode. That means, in other words, you can see that there is increase in the mass of the electrode at the cathode electrode, and there is a decrease in the mass of the electrode at the anode electrode during the electrochemical process. Here if you go for redox reaction, of course here also almost it is same. So here if you take anode, it is positive sign convention. It is cathode, again here it is reverse, it is negative sign convention. So here again it is participating in the oxidation, and here it is participating in the reduction reaction. Only thing is that you are finding that there is a change in the sign convention. Here the process, electrochemical process, always it goes to completion, goes completion, goes to completion by connecting two half cells to salt bridge, to a salt bridge, and the two half cells should be connected externally to the voltmeter. It contains a voltmeter. Connecting the salt bridge is equally important, and connecting the two half cells through the conducting wire to the voltmeter also, it is equally important. And at the same time, here the reaction goes to completion by connecting both the electrodes to the battery. Okay, completion is done by connecting the two half cells, connecting two electrodes to power source. Fine, this is the differentiating table. From this differentiating table, actually electrochemical process is studied through galvanic cell, or it is also called as voltaic cell, or sometimes this galvanic cell or voltaic cell is a part of Daniell cell. So whatever may be the case, if you go for galvanic cell, if you take two half cells, this is the first half cell and this is the second half cell. First half cell, second half cell. In the first half cell, we just try to take the solution. Left side we take it as, this is zinc sulfate solution. This is zinc sulfate solution, aqueous, and here we are going to place an electrode. We are going to place an electrode, zinc electrode, and here we take the vessel, that is copper sulfate, and here this is copper electrode, and here you take the conducting wire and you connect it to the battery, which is equivalent to 1.1 voltmeter. So here what we are noticing here is something like, here this is zinc electrode and this is copper electrode, and here this zinc electrode is given a sign convention, negative sign convention, and copper electrode is given a positive sign convention, and of course we try to connect it through a salt bridge. It is mixed with the agar-agar jelly at the two openings, and the salt bridge is filled with the salt of potassium nitrate. This is salt bridge. So this is the salt bridge. Salt bridge always maintains the electrical neutrality. Allows the migration of, it prevents the migration of ions, but you find that whenever there are excess charges, the excess charges are neutralized by the movement of the K plus ions and the nitrate ions. They try to move in the opposite sides whenever there is an excess of ions present in both the half cells. So that is the main purpose of introducing salt bridge. Now here this portion, I am going to cut this into two halves. I am going to cut this diagram into two halves. On the left side, this is left side and this is right side. So this is left hand side. I will take this as left hand side, and this I will take it as right hand side. So left hand side I am going to take oxidation half reaction, oxidation half cell I can take, and right side I will take reduction half cell, RSC. Then you find that because oxidation half cells involves oxidation and reduction half cell involves reduction. So that means because both the half cells are separated through salt bridge, so this salt bridge is given by a double vertical line. So if I write the cell notation, so suppose if I want to write the cell notation for the electrochemical cell, then I can just take it like this. I can just take here the metal is getting oxidized, M2 plus ion, aqueous, double vertical line, and again here the metal is getting reduced, so therefore M2 plus of aqueous, double vertical line, metal. So this vertical line represents the salt bridge, and the concentration of both the ions, here this is getting oxidized and here it is getting reduced, and this is nothing but the salt bridge. And sometimes they are also given concentration, both the metal ions, which are the metals which are getting oxidized and the metals which are getting reduced. In both the cases you find that the concentrations are given. Then if concentrations are given, then we have to express the concentration also for the given electrodes. So here if you go to the galvanic cell, so let us continue a discussion like this. Working of galvanic cell. If you go to the working of galvanic cell, what we are going to notice here is, take the two half cells. First half cell, this is the first half cell and this is the second half cell, and here you try to place one electrode, zinc electrode, and here you try to place an electrode, that is copper electrode, and here you are trying to fill the solution, zinc sulfate solution. This is zinc sulfate solution separated through a salt bridge. This is salt bridge in the meantime, and here you try to fill the copper sulfate solution. Increase the height of the metal plate. Okay, so this is copper sulfate solution. So if this is the copper sulfate solution, then externally we are connecting both the half cells to the voltmeter, which must be equal to, that is, which must be equal to less than 1.1 electron volts. 1.1 volts should be always less. So the potential difference or the voltage should be always less than 1.1 volts. So what we are noticing here is, because zinc is more reactive, based on the reactivity series, if you go to the reactivity series, you find that zinc electrode H plus of 1 electron, reversible reaction, half mole of H2 gas, semicolon, platinum of, that is electrode potential, its standard electrode potential is equal to plus or minus of 0.00 volts. So it is interesting to find that zinc is an electrode which is present in the above the hydrogen electrode. This is standard hydrogen electrode. This notation which I gave is for standard hydrogen electrode, SHE. So above the hydrogen electrode you find the active electrode system, that is zinc electrode system, and below the hydrogen you find that it is copper Cu2 plus 2 electrons, reversible reaction, that is copper. So you find that here, because zinc is above the hydrogen and copper is below the hydrogen, zinc is more active electrode. This is active electrode system, and this is more active, greater active, and this is less active electrode system, So that is why what we are doing here is perfectly, we are just giving the designation of the electrode convention for the zinc electrode is negative, and here the electrode convention for the copper is positive electrode. And what is happening here is, as the electrochemical process begins, when the potential difference between the two half cells, this is oxidation half cell, and this is reduction half cell, when the potential difference between the two half cells is less than 1.1 volts, then you find that immediately the zinc it starts dissolving into the the zinc electrode plate gets oxidized. When it is getting oxidized, it starts melting. That means the plate starts melting. When it is melting, you find that the melted mass of the electrode plate, the zinc ions, goes into the solution like this, Zn2 plus ions. As the electrode plate thickness is decreasing, you find that the zinc is getting oxidized. When it is getting oxidized, the zinc ions goes into the solution, and the free electrons which are obtained, they start traveling. You can see these dots. These are the electrons which are moving from the zinc electrode to the copper electrode. So this is the path of the flow of electrons. Electron flow. This is electron flow, and these electrons, they reach the copper electrode, and here already this copper contains cupric ions. Here they have cupric ions. These cupric ions, they try to accept the electrons. They accept all these 2 electrons are accepted by the some more and more number of free electrons. They start moving from the oxidation half cell vessel to the reduction half cell vessel, and these free electrons are being captured by the cupric ions. So these cupric ions, they capture these 2 electrons, this bivalent, and they get reduced. Once it is getting reduced, you find that the cupric ions which are getting reduced to copper, they get they move towards the electrode plate, and you find that there is an increase in the mass. There is an increase in the overall thickness of the electrode plate. So this, I can say that here the copper is deposited. Copper is deposited, there is an increased mass, and here the zinc is melted, or the zinc is melted. Okay, there's a decrease in the mass. Instead of melted, let me say the zinc mass decreases. The thickness of the zinc plate decreases, and here the thickness of the copper plate increases. So therefore, what we are able to understand here is, from this it is very clear that, and in the meantime, what is happening to the salt bridge? Salt bridge contains K plus and NO3 minus. Here it is filled with the openings of the 2 ends of the salt bridge. It is filled with agar-agar jelly, and it prevents the migration of ions, and it also maintains the electrical neutrality. When more and more amount of excess zinc ions are going into the solutions, then sometimes the electrochemical process may stop. So to prevent the process from stopping altogether, immediately you find that the opposite charged nitrate ions, so from this KNO3, the nitrate ions will migrate towards the oxidation half cell, and potassium ions will migrate towards the, that is copper sulfate solution, that is cupric ions, and they maintain the electrical neutrality, and they see that there is a continuous electrochemical process taking place. In the meantime, we are discussing about the cell notation, or the completion of cell notation and the completion of the electrochemical process. So what is the cell reaction taking place? If you go to the cell reaction in electrochemical process, if you take cell reaction in electrochemical process, if you take in the oxidation half cell, so I will take like this, in OHC oxidation half cell, the zinc mass of the zinc electrode plate is getting oxidized, so zinc solid is getting oxidized to Zn2 plus 2 electrons, and in reduction half cell, the cupric ions are getting reduced to copper. So here add 2 electrons, reversible reaction, copper solid. So what is happening here? 2 electrons, they get cancelled. So this is Zn2 plus zinc plus Cu2 plus aqueous, reversible reaction, Zn2 plus of aqueous plus copper solid. So here this is the net reaction. So these two have to be, this is the overall reaction. Let me say this is a first equation, this is second equation, And now this is third equation, this is overall reaction of the electrochemical cell. In the overall reaction, again if you convert into cell notation, if you are converting this reaction into cell notation, converting this to cell notation, so Zn single vertical line, Zn2 plus of aqueous, again double vertical line represents the salt bridge, and again cupric ions are getting reduced to, that is copper. So you find that this double vertical line, the long double vertical line represents the oxidation half cell, and this represents the reduction half cell. This is oxidation half cell, reduction half cell, and this is salt bridge. So this is the cell notation what we can take for the electrochemical process. So here the next part of the discussion is, that is conclusions from electrochemical process. Conclusion from the electrochemical process. The first conclusion is, that is the first conclusion is flow of electrons. Flow of electrons are always from oxidation half cell to reduction half cell. Next is flow of current is reverse. Flow of current is from reduction half cell to oxidation half cell. Next is the power source, that is the voltmeter. The voltmeter should always have a potential difference equal to less than 1.1 electron volts. Potential difference must always have, the potential difference must be equal to 1.1 volts. You can take 1.1 volts. If it is equal to, if the potential difference, yes, electrochemical process continues. Electrochemical process will continue. But if the potential difference between two half cells, that is potential difference is equal to greater than 1.1, then the process is reversed. The process is 1.1 volts, then the process becomes electrolytic process. The process becomes electrolytic. Between two half cells, the potential difference between two half cells, if it is equal to 1.1 volts, no reaction occur. The reaction stops. No electrolytic reaction, no electrochemical reaction. Both the reactions will stop. So these are the conclusions where we can make. And one more thing what we have to understand is, because we are using the word potential difference, actually this potential difference is given by, that is capital E of the cell. When you say capital E of the cell, this is called potential difference of electrochemical cell. Potential difference of electrochemical cell, and if it is the potential difference of electrochemical cell, then we can use the formula potential difference of the cell, electrochemical cell, is equal to standard electrode potential of cathode minus standard electrode potential of anode electrode. So we can also take this as E naught of reduction half cell minus E naught of oxidation half cell, because you know pretty well that the oxidation half cell belongs to anode electrode and reduction half cell belongs to cathode electrode. So that's why we are using this formula, that is potential difference, potential of the cell is nothing but standard electrode potential of the cathode minus standard electrode potential of the anode. So here when you are saying potential of the cell, it belongs to the complete electrochemical cell. And this actually E stands for electromotive force. Electrochemical cell is nothing but electromotive force. This electromotive force is the potential difference which is operating between the two half cells. And one more important aspect here is, that is calculation of potential of cell calculation of potential of cell for the oxidation of cell for anode and cathode. Let me put it in this way, anode and cathode. So here if you take, usually the potential difference, the electrode potential sign convention, electrode potential is always taken in terms of electrode potential of electrodes is always taken in terms of SRP values. So what are SRP values? SRP means standard reduction potential values, standard reduction potential values. Sometimes we also use SOP. SOP means standard oxidation potential values. What is the difference between SRP and SOP? Always SOP, standard oxidation potential, is minus of standard reduction potential. If any electrode potential is having, if any electrode is having high value of oxidation potential, then it also has low value of reduction potential. If the oxidation potential is positive, the reduction potential is negative. Suppose if I am taking, if plus 1.87 is the standard electrode potential, if plus 1.87 is the standard electrode potential of SOP value of the fluorine electrode, then for SRP it is going to become minus of 1.87 volts. This is what we have to keep it in mind in terms of SRP and SOP. Only the sign convention changes, but the magnitude of the value remains same. So here, that means from this what we are able to observe is the calculation part is very important, and that's why when you are taking this SRP, that is SRP value greater negative, more negative, SRP value with more negative, standard electrode potential for an electrode system with more negative value is always taken for anode, and SRP with the less negative value expressed in volts is taken for cathode. That means I mean to say, if both are negative, if both the values are negative for anode and electrode, the more negative value always goes for anode and the less negative value goes for cathode. Similarly, if you take the SRP value, SRP for a given electrode expressed in volts, SRP expressed in volts for given electrodes, we can take for anode. For anode, if it is positive value, more positive goes for cathode, more positive always goes for, less negative means more positive goes for cathode, and here cathode it is more negative means less positive, more positive goes for anode. Okay, already we have written there, no problem, so this is not required now. So more positive goes for anode and less positive goes for, that is, cathode. So this is what you have to keep it in your mind when we are trying to solve different problems based on the electrochemical cell. So here, if you look into the question here, one small question let us try to do. Write the cell reaction for the following pair of electrode systems. So this is one pair of electrode system. Here the electrode system is, one is, here it is zinc electrode and here it is, that is, nickel electrode. So assigning the sign convention is very important. So what we are observing here is, you find that this minus 0 points between the electrode systems for the zinc and the nickel, you are finding that for zinc electrode the the potential difference is minus 0.76 volts, means it is more negative. So more negative, as already I told you, more negative should be always, it should go for anode electrode, and minus 0.25 volts is less negative value. So I am just taking this for cathode, and don't forget that here both the electrode systems of zinc and nickel, they are expressed in SRP system, reduction potential system. You are finding that the zinc is getting reduced to, zinc ions are getting reduced to zinc, and nickel ions, Ni2 plus ions are getting reduced to, that is nickel. So both are in the SRP system only. So for the SRP system, with respect to two electrode systems, so take the formula, potential of the cell is equal to potential of the cathode minus standard electrode potential of cathode minus standard electrode potential of anode. So here I am taking that is for zinc electrode, if I take for zinc electrode, if I am taking money, that is for nickel electrode, sorry, for this is cathode, so minus 0.25 volts, cathode is minus 0.25, then here for anode it is minus 0.76 volts, so this is going to become minus 0.25 plus 0.76, so 0.76 of 0.25, this is 1 and this is 5, so 0.51, so this is going to become plus 0.51 volts is the potential of the cell. That is for the first case with respect to zinc and nickel electrodes. Now similarly with respect to copper and silver electrodes, if you take, so again potential of the cell is equal to standard electrode potential of cathode minus standard electrode potential of anode. If you take, so if that is the case, here more positive always goes for, more negative means less positive, so less positive must go for anode, so more negative is always anode, more negative means less positive means this is less positive means this should be definitely going for anode, and here more positive always, so cathode it is less negative means more positive, so more positive should go for cathode, so therefore more negative less positive, yes, anode more, this is more negative, so less positive means anode, this is less negative means this is more positive. Of course it's not exactly comparison, but the higher positive value should always go for cathode and lower positive value should go for anode. So if that is the case, take these values, substitute it. For cathode we have plus 0.8 volts, minus for anode you have 0.34 volts, so therefore you can take 0.8 of 0.34, so this is going to become 6, this is going to become 5, this is 1, so this is 0.26, so this is actually 7, so 7 means this is going to become 4, so this is plus 0.46 volts is the answer. And also you can write the cell notation. If you want to write the cell notation for the first case, you want to write the cell notation, take the cell notation for the first case. If you want, zinc is at anode, so therefore I will take zinc solid, okay, Zn2 plus of aqueous separated by salt bridge. Again nickel is getting reduced, so Ni2 plus of aqueous single vertical line, that is Ni solid, is the cell notation for the first electrode system. For the second electrode system, if you want, we can write the cell notation for the second electrode system, that is you can take here, that is here copper is getting oxidized and silver is getting reduced, so therefore here we can take, yes, copper if you take Cu, copper is getting oxidized, so Cu2 plus double vertical line Ag plus single vertical line Ag, so you can just think that this is oxidation half cell and this is reduction half cell. Here also this is oxidation half cell and this is reduction half cell. So in this way we can convert the cell notations, and if you want we can even write the cell reactions also, and then we can write the overall cell notation, we can also write the cell reaction. So now let us write the cell reaction for both these electrode system pairs. So for first one A, for a cell reaction, if you take electrochemical cell reaction, if you take zinc is getting oxidized, so I'll take zinc solid reversible reaction, that is Zn2 plus, I think okay, I'll just take it Zn2 plus aqueous plus 2 electrons, then it is getting oxidized, zinc is getting oxidized, then if you go for nickel, it is getting reduced because anode and this is cathode, so I'll take this as Ni2 plus of aqueous, Ni2 plus of aqueous plus 2 electrons gives rise to reduction Ni solid. So if you add both these equations, you find that you can just cancel these 2 electrons here in the oxidation half cell and reduction half cell reaction, then write the net equation. Zinc solid plus Ni2 plus of aqueous reversible reaction, you can take, that is zinc 2 plus of aqueous plus nickel solid is the reaction what we can take. This is the overall reaction. This is overall cell reaction. This is the final equation. If you go for the second part, that is copper and silver, if you take cell reaction, take the cell reaction. So here if copper is getting oxidized, copper electrode is getting oxidized, so copper solid gives rise to cupric ions, aqueous plus 2 electrons getting oxidized. So here if you take silver, it is getting reduced, so Ag plus plus 1 electron gives rise to Ag. Of course we need to add because the first equation here it is de-electronation and this is reduction electronation, so you have to multiply the second equation with 2. So when you are multiplying the second equation with 2, instead of 1 electrons you are supposed to take 2 electrons, and this is going to become 2 moles of Ag solid. So now you have to add both the equations. When you add 2 electrons gets cancelled, so copper solid plus 2 moles of Ag plus of aqueous reversible reaction, so you get over here, that is 2 moles of Ag solid plus cupric ion, that is aqueous, is the cell reaction for the second case. So in this way we can write the different cell reactions depending upon the different electrode pairs when they are in the standard reduction potential system of the reactivity series. So here the next part of the discussion is, that is Nernst equation, for that is metal and non-metal electrode, metal and non-metal electrode systems. So here first of all let us go with the Nernst equation for metal electrode system, for a metal electrode system. So if you are going for metal electrode system, one thing what we have to understand here is, that is note both metal and non-metal electrode system are in SRP, standard reduction potential values. Okay, they are expressed in SRP method. So what do you mean by this actually? So suppose, because we are already saying that it's a metal electrode system, so I'll write one equation. In fact, if you want to calculate the potential for metal electrode, let me give you one more point here. So to calculate the potential, electrode potential, to calculate the electrode potential of half cell, we have a generalized formula, that is E is equal to E naught minus 2.303 of RT by NF of log, that is product concentration divided by reactant concentration. Or you can just write this in much more simpler way, that is potential of the half cell electrode is equal to E naught minus, this is, if you substitute the value of gas constant, R is the universal gas constant and T is the temperature. If the temperature is 25 degrees centigrade, which is equal to 298 Kelvin. If R is the gas constant, 8.314 joules per mole per Kelvin you take. F is the Faraday's constant, which is equal to 96,500 coulombs, and N is number of electrons involved in that is de-electronation or electronation of electrode systems. So that is the case. By substituting and simplifying all these values, that is, substitute all these values and simplify, this expression finally turns to be 0.059 by N. Substituting, simplifying and getting the final expression 0.059 divided by N into log of concentration of the products divided by concentration of the reactants. This is what you are supposed to remember. So that's why for the metal electrode system, let us write the generalized equation. So therefore here for metal electrode system, we write the generalized equation. If a metal ion is carrying n number of positive charges, it gains n number of electrons and it forms metal solid. This is metal ion. So this is metal ion. Metal ion carrying n number of positive charges gains n number of electrons to give metallic solid. So this is for metal electrode system, and we will apply this metal electrode system and we will try to substitute in this equation, and let us try to get the final expression for the metal electrode system. So here for metal electrode system, let us write the general equation. If a metal ion carrying n number of positive charges in the aqueous state, if it is gaining n number of electrons, it is getting reduced to metal solid. This is metal ion and this is reduced metal. So and this is in this metal ion concentration, it is in the reactant side, this is in the reactant side, and this is in the product side. So take the formula, potential of the cell is equal to E naught minus 0.059 by N of log concentration of the products divided by concentration of the reactants. P for products, R for reactants. So therefore again this is going to become E naught minus 0.059 by N of log product concentration is metal, reactant concentration is metal ion. So this is metal ion, M plus ion. And again, if I change the sign, one more thing, here at 25 degrees centigrade is E naught minus 0.059 by N of log the concentration of metal ion in the neutral state, the concentration of the metal in the solid state, its concentration is 1, because for solids the concentration is always, its concentration is equal to 1, that is unity, because for solids the concentration is always 1. So the metal ion in the aqueous state, so therefore if I change the sign, if I am going to change the sign, then this is going to become E naught. If I take minus of plus, then this is going to become 0.059 by N of log metal ion concentration. So this is the final expression which we need to remember. So this is the expression, this is the Nernst equation or Nernst equation expression for metal electrode system. So similarly, let us go to the second one, that is Nernst equation for non-metal electrodes. If you are going for non-metal electrodes, again let M be a non-metal, it is gaining n number of electrons, it becomes Mn minus of aqueous, this is non-metal, this is non-metal ion, so these are the reactants. These are the products. So therefore here again take the expression, so E is equal to E naught minus 0.059 by N of log product concentration divided by reactant concentration, product concentration divided by reactant concentration. So E is equal to E naught minus 0.059 by N of log. So here in the product we have metal ion concentration Mn minus, okay, in the reactant side M, it is in the neutral state, so its concentration is 1. So therefore E naught minus 0.059 by N of log, that is metal ion, non-metal ion concentration divided by 1. So therefore E is equal to E naught minus 0.059 by N of log non-metal ion concentration. So this is the final expression we use for calculating the Nernst equation for the non-metal electrodes.